Hi, everybody. This is our last lesson for Unit 4, and it's about power and universal gravitational potential energy. So it's kind of a new way to think about potential energy on more of an astronomical scale. So this is technically topic 4.4 and 4.5. Okay, so the first thing to talk about is power. The definition of power is the rate at which work is done. Power is given the capital letter P, and the unit is going to be the watt. Okay. And watt is shortened to a capital W. So the rate at which work is done, our equation for power is going to be P equals work over some change in time. Work is just a change in energy, so you can think about that as just how much energy is being converted or used over some amount of time. Okay. All right, for you calculus people, power is the derivative of energy with respect to time, if you guys like little calculus connections. There is another equation for power. So if you remember the equation for work, work is just a force times a distance, as long as we're not doing something at a weird angle. So power is actually going to be force times distance over some change in time. And distance over change in time, that's just speed. So another equation for power is force times speed. So two equations. You can use whichever one you want as long as it makes sense with the question. So I'll show you how you can use either one for this equation down below. So a 60 kilogram jogger runs 4.5 meters upstairs in 4 seconds. So we've got someone jogging. They're going up some stairs, a height of 4.5 meters. What is the power required? So let's start with our first equation. Power is the change in energy over change in time. Let's assume that he is running at a constant speed, so he's not changing his kinetic energy, but the type of energy that he's changing is his potential energy. So my change in energy is going to be my change in potential energy over change in time. So that's going to be mass times g times my change in height over change in time. So let's plug in what we know. We know that the mass is 60 kilograms, g is 9.8, and we're changing our height of 4.5 meters over 4 seconds. So the power required is 660 watts. So if this person had run up these stairs at a faster rate, then that would, we'd be dividing by a smaller number here, so it would require more power. So even though the change in energy is the same, it could require more or less power depending on how quickly we go. Thinking about this other equation, force times velocity, or speed, you can kind of see that up here. So the force, as this person is going up the stairs, he's got weight. He also has to be applying some upward force. Okay. Again, if we're moving at a constant rate, our upward force is going to equal the weight. So our force here is just mass times g, and speed is some distance here. So that's our change in height over change in time. So this quantity right here is that v. So really, both of these equations are equivalent. All right, so the next thing we're going to hop into is talking about a different way to think about potential energy. So the potential energy we've talked about so far is mgh. This is assuming that this g is constant. So that means we're staying relatively close to the surface of a planet or a moon, something like that, but we're in a relatively constant gravitational field. So even if you're on the top of Mount Everest and you throw something down to sea level, still a relatively constant gravitational field. But if we're getting into situations where we're leaving the surface of a planet or getting much further away, we have to have a new way to think about this. And the new way to think about it, it's still potential energy, gravitational potential energy, so it has the same UG, but our equation is going to be negative, and I'll talk about that in a second, big G, M1, M2 over R. So it's kind of the same as, we're reminiscent of force is G, M1, M2 over R squared. Okay. We just got rid of the squared. It's just a single R right here, and it is negative. So, and make a note here, this is for astronomical, can't spell, situations. Cool. All right, so why is this negative? Okay. So I'm going to try to explain that. If we have our potential energy with respect to distance, this relationship is a negative, essentially reciprocal graph. It looks something like this. Okay. So if you imagine, if you are infinitely far away from a planet, so think about planets in another solar system, super, super far away, where R is essentially infinity, that is where our potential energy is 0 when R essentially approaches infinity. Okay. So I know that when I get infinitely far away, I have to have no potential energy. Okay. But as I get away from a planet, I have to do positive work. So for this little rocket ship here to go from point A to point B, I need to add energy. Okay. So I need to do work here. So that reflects on the graph here. Say this is point A right here, and this is point B. I have to do positive work to get away from point A to point B. So this has to be a positive change, and that can only be seen if this graph has this sort of shape. And again, work is my change in energy. I am doing positive work here, so I need to be increasing my gravitational potential energy, but I still need to be able to get to 0 infinitely far away. Hopefully that made sense. If not, shoot me an email. Let's do an example. All right, so this is about escape velocity. So what is the minimum speed you'd have to throw a ball? So here you are on the surface of Earth, and you want to know how fast you have to throw a ball so that it just keeps going and does not fall back to Earth. So let's set up our conservation of energy statement. So initially, I know I'm going to have some sort of kinetic energy. Sorry, dogs are barking. And I'm going to have some gravitational potential energy. And I'm trying to figure out what the minimum speed is. So I essentially want to throw it just hard enough so that when it escapes any measurable pull of Earth, it's not moving anymore. Okay. So I'm going to have no final kinetic energy. And I'm also going to have no gravitational potential energy. I'm essentially getting far enough away that we're in this realm over here where we have no potential energy. So the ball will not fall back down to Earth. Okay. So let's set up these equations here. So I've got 1/2 mv squared plus my new formula is negative g mass 1 mass 2 over r. And this mass 1 is going to be the mass of the ball. And mass 2 is Earth. We're trying to get away from that gravitational potential energy created by Earth. Let's set those two equal. So 1/2 mv squared equals positive, because we just added it over, m1 m2 over r. Mass of the ball doesn't matter, so this could be for a ball, or how fast would a rocket have to blast off to escape the pull of Earth. And we're solving for v. Things we need to know: the mass of Earth It's about, got it right here, 5.97 times 10 to the 24 kilograms. And the radius of Earth is 6.38 times 10 to the 6th meters. So if we plug those in and rearrange this to solve for V, so let's multiply the 2 to the other side. 2g m of Earth over r of Earth, and take a square root. If we plug in what we know, so 2, we know g is 6.67 times 10 to the negative 11, mass of Earth, all over the radius of Earth, still under the square root. Just getting a little messy, sorry. Comes out to a pretty big number. It's 1.1 times 10 to the 4th meters per second. That ends up being about 25,000. So about 25,000 miles per hour. So if you were physically able to throw a ball at 25,000 miles per hour, it would go out into space and not fall back down. There's no homework assignment for this specific unit. There is